Hello everyone, this is Olivia. In this video, I will introduce our second task, data mining task, regression model building and evaluation, or in general, it is called regression analysis. Um, Before I talk about the um, topics or agenda, let me first quickly distinguish regression analysis from classification, which you already are very familiar with from the last 3 weeks or 2 weeks. Regression modeling or analysis is very similar to classification in that it predicts the value of a target variable, or it is also called dependent variable, sometimes called response. And however, the difference is in classification, the target variables can strictly be categorical or nominal. And here in regression, we focus on target variables that have numerical, like integer or real number or real values or continuous values. Okay. Um, the main, a good reference out of our two books for this um, task is your machine learning with R book, chapter 6 on regression. And that chapter, as well as other chapters, covers a number of common methods used for building regression models. To start off with, in this chapter, we'll focus mostly on linear regression and using multiple predictors or single predictors. The function in R package is in R is LM. Also, this regression model can be compared to a couple other hybrid models, regression tree, model tree. These are decision tree based from two other packages, RPart and RWECA. In the next couple weeks, we will start to cover other methods for both classifications and for regression analysis. And the methods SVM, neural network, and KNN can also be applied for regression. If we have time, we definitely would like to go over code and include them for your practice. So today, mainly we focus on linear regression models for the most part. Linear regression has a long history in statistics. Even though we're here primarily to apply, we need to understand certain statistical principles and that even are applied to not only build models, but also used to measure models' explanatory power as well as predictive accuracy. So as for data science, we need to put a lot of focus on what are the important questions that a data scientist should think about. And to answer those questions, what are the appropriate evaluation metrics? So these questions and evaluation metrics are divided into two groups based on their purpose, different purposes. Explanatory purpose and predictive purpose. So in order to avoid overfitting, we also want to use model building and evaluation approaches that would allow us to assess the differences in performance of a model over different test sets or holdout sets. So this part is a refresh of what we have covered, but since this is it's only been a couple assignments on model building and evaluation, so I will also go over this to strengthen the concepts. And some of these concepts, you will see them in practice and being explained by Yuan Yuan in her videos on our on R for building linear regression and hybrid models. And so if we don't have time, um, uh, then some of the concepts I would highlight them only. And no matter what, comparing two videos or two set of slides will always be helpful. Linear model is about building a line, and so the first concept we need to learn and or refresh our memory of is the basic construct of a linear model or a line. Using a single predictor and for a single target variable, then single linear regression or simple linear regression, abbreviated as SLR, can be formulated as predicting Y or estimating Y using a formulation of a constant or called Y-intercept plus B or beta, the coefficient for the predictor X. So Y can also be written as alpha plus beta times X. These are some of the common notations. And beta is, we already mentioned that A is Y-intercept, which is the Y value for when X is 0. Beta is the slope of the line, which is the amount of change in Y divided by the amount of change in X. Or in another word, it means that for every unit of change in X, the amount of Y change is expressed in the slope or beta. This is the formulation, and this is quite important when it is used to understand the relationship between X, a predictor, with a target variable Y. So the beginning of any data mining should be data. So we will also start the discussion of how to derive a line to fit data. That's the meaning of regression, fitting a line to data using a set of data. In chapter 6 of machine learning with R, there is a very sad example based on that was motivated by the Challenger disaster. Prior to Challenger's explosion, there were 23 event shuttle launches, and parts failures were recorded. And this particular data set were concerned with the failures of a part called O-ring in the engine, and the count of values of none for 0 given different temperature during launch time called launch temperature, and or some value of 1 O-ring, even value of 2 were recorded. There are a total of 6 O-rings in Challenger, so less than 6 could potentially still the engine could still be functionable. Of course, more distress events is more risky. So with this, we can start to use this example to help us think about some important questions. For example, similar to classification, one will ask, can we use temperature to predict distress event? From linear regression models point of view, then the question should be reduced to, is there a relationship between temperature and stress event? And also furthermore, is this relationship aligned or close to be aligned? Okay, so this is we can manually try different lines, and this is a line that was has already been learned using ordinary least square method, where the y-intercept is 3.7. Note that 0 is somewhere here, so 3.7 is further up there as we extend the line this way. And the slope is negative 0.048 per change or per unit of temperature. So distress event increases as temperature drops, and that was that was a somewhat of a hypothesis, because during the launch of this Challenger, the temperature was lower than 40 Fahrenheit degrees, and these are the um, data that were added to the original data based on using this line. So for every x value on this temperature using this original data set, then we can come up with predictive value. It's not integer counts, but continuous value. And using this predicted value and actual value, we can start to measure their errors. The blue dots on this line are the predicted distress event count or distress event value based on the actual based on the value of x, and the black dots that are linked to this blue are the actual value in the original data set. So these red lines measure the amount of error. The error is called also residual of a point when you try to fit this point, this x to this line, and there is some amount of y that cannot be being included in the predictive value. So this is called residual. And this residual can be positive or negative, like in this case. So a lot of time the errors being multiplied by itself, so that we take the square residual and they all become positive for further calculations to evaluate the performance. So now we can talk about the method that is used, that can be used to derive the line. The most common one, ordinary least squares, and relatively more straightforward to understand. The derivation of y-intercept A or alpha and the coefficient estimate for the predictor x, b or beta essentially are derived by a method to minimize the sum of square residuals, RSS, or the sum of square error, SSE. Both of these are the same. We just use this notation only. And the sum of square, essentially, in the previous slide, these are the each cell here is square residual. So the sum of this is what this method trying to minimize to come up with beta coefficient estimate and come up with y-intercept. Beta will come first by using covariance of x, the predictor, and target variable y, and covariance is calculated using the difference of x value from x mean, and the different multiplied by in the same point the y coordinate value minus y mean, and this is divided by the variance of x variables. Okay. And building that model can give us an idea of the relationship between two variables, and Pearson correlations using this formula, which is somewhat similar to the previous one, where this is also covariance of x and y variable, but the denominator is sigma, which is the standard deviation of x multiplied by standard deviation of y. And this is a measurement of how two variables, x and y, how their relationships is closely following a straight line. And the value can range from -1 to +1, and closer to -1 and +1, it means that the relationship is linear or perfectly linear or almost linear. Whereas when the value is 0 or close to 0, indicate that there's no linear relationship between two variables. So when y is your target variable and x is your predictor, this can give you an assessment of how whether these two have the predictor has a linear relationship to the target variable, and how strong that linear relationship is, and can give you an indication of whether x can be a good linear predictor in a linear model for y. Sometimes this is also very useful, like we have in various assignments, to see the correlations amongst predictors themselves. So if two x's or x and y both are predictors, and Pearson correlation can indicate how closely they are related. And if they are, then we have a collinearity or a multicollinearity phenomena, which essentially is a phenomena when the two predictors like x and y are closely related, like in this case where their values are overlap, so that high correlation Pearson correlation coefficients will be there positively or negatively. And that indicates that we can use this predictor to easily linearly predict or estimate the other predictor, and which this case is not. If there are no strong or presence of linear relationship, then x and y are relatively more independent. So if we go back to go here, we go back to the Challenger example, 23 points. In the data set itself, actually, there are 4 variables besides the y distress count, the predictor temperature, there's one other predictor, field check pressure, and also there is a record number, which just flight number. And so the focus should be on these 3 variables. This diagram is a diagram of both correlation coefficients, histogram, and also scatter plots of the 2 pairs of variables. So if we look at the relationship of temperature as a predictor to distress count, and the other predictor called field check pressure, these 2 values are their Pearson correlation if coefficients to distress count. So this is negative, higher than 0.5, lower than what was in the book before. But using the data, this is actually what I got from Pearson correlation coefficient function. And but nevertheless, compared to this field check pressure, it seems to have a higher, has a higher relationship to distress count, whereas this one is lower. More importantly, if we look at the relationship between this temperature predictor and field check pressure predictor, this number is their correlation, which is close to 0, and that indicates that these 2 don't have linear relationship. You cannot predict or estimate one using the other, and so there's no collinearity between the 2. Even though there is a very strong one between flight number and field check pressure for some reason, given that we typically don't use a flight number, a unique case identifier or record identifier like flight number in our predictor, we don't also need to worry about it. So now we're ready to apply ordinary least square method to derive a line the line we saw for this small example, the function which Yuan Yuan will go through in more detail is LM for linear method, and the formulation is the Y distress count is model as using temperature. The data set is challenger. These are the output that you will see when you use the function summary of the model that's built using this. And their various parts are useful to understand. And in order to understand how you use or how the meaning of the different parts of the model, such as this Y-intercept, this temperature, but this beta coefficient estimate for temperature, and the p-values, overall R square, adjusted R square, and F statistic. Let me then move on to talking about the questions that one would like to answer using model output or model summary, and how what evaluations or what metrics or model elements we can use to answer those questions. The group of questions for explanatory models or that are related to a model's explanatory power are this, and these are primarily concerned with whether and how well whether a predictor explains the impact a predictor affects a dependent variable and affects it significantly or not. And once we know that, then we can answer the other question, and which predictors actually do affect the dependent variable significantly. So questions related to this purpose is, like before for Challenger, is there a relationship between a predictor like temperature and the target variable like distress count or O-ring values? Is this relationship linear, and how strong is this relationship, which we haven't talked about much? Is it, if there are multiple predictors such as the field check pressure, is this linear relationship stronger than the relationship between another predictor and the target variable? But also, once you have multiple predictors, there are also interesting questions such as that even though if two predictors could have their own separate impact or relationship to the target variable, but when these two variables values change simultaneously, that whether they have joint effect or a joint relationship with the target variable. So this is kind of interesting, and to model this type of synergy and to test this type of synergy, we should use interaction terms between two predictors, such as multiplying the two together. We can see that in an example in the tutorial in the book, and which Yuan Yuan will go over. And there is always somewhat of an overall question, such as, does the model fit the data well, or what is the fitness of the model? And from a prediction point of view, or from a overfitting, based on the concern with a model or a line overfitted to data, then we should always ask questions similar to those that we ask in classification, that whether the model can be general or can be generalized across different data sets. So these are the some example questions when we are more focused on explanatory power, and the elements and metrics that are used to answer these questions include the beta coefficient estimates, the Pearson correlation coefficients we look at. We haven't talked about p-values and R square, and a little bit of F statistic. and we will use some formulation to introduce R square more, and then talk about p-value and F statistic uh, a bit. So R squared and adjusted R square are very important parts of uh, the answers to whether a model fit the data well or not, whether the model can explain the variances well. Formula is, again, based on a sum of squares or sum of the variances or sum of the errors, if you remember. And these are the errors between y value and y mean. And, this is the total sum of square errors in the actual data. But once you make an estimation, then we also can get the sum of estimated um, y value and the actual y value, which were in our table before. And this ratio essentially is our R square. And the meaning is that the percent of variances in y can be explained by the predictors, the y estimates. Um, that multiple R squared or R squared is also in another formulation is adjusted to adapt to the higher number of independent variables or predictors in the model. So we tend to see that number drop either for a larger a model with large number of variables, or the variables, some of the variables don't have explanatory power, such as or the power itself is low. Okay. So using Y, using R, we can come back to this result where residual standard, where multiple R squared is here and adjusted R square. Here are one is 0.26 and adjusted came down partly because the explanatory power of the predictors are not as is not as significant. The other part of the fitness of model that one should also consider is this F statistic, which is a value that when it is higher or further away from one, the better. But actually, how far, how large F statistics is sufficient to indicate model fitness. It depends on some other parameters. One is the overall F value in the estimate calculation for the derivation of the linear regression model. The other one is the number of cases minus 2, which is 23 cases minus 2 is 21, we call degrees of freedom, as well as the number of variables or predictors, which is actually 1 here, and we call 1. So this are F statistic actually test that if many of the predictors in a model where there's more than there's just one or several, it will start to consider that whether if their coefficients are actually 0, that how likely that will happen. And so this F statistic follow F distribution with these parameters. So there is F table out there, can look up. Basically, if we look it up, you'll find this F statistic for this particular model is on the borderline of a fit, a model with good fitness of that fits the data well. R square is also kind of depends on what kind of application. For mission critical application, I think this could be concerning. Coming back to this part of the model, this is the Y-intercept and beta coefficient. Essentially, the beta coefficient is indicating that when a unit of temperature change, this is the amount of change in Y, which is distress count. So this is a very useful interpretation of how the relationship between temperature and target variable distress count. But in interpreting this value, it's important to look at what is called p-value. That is this probability that the actual estimate is higher than this t-value, which is the multiples of this estimate is this indicates how many times of standard deviations this estimate is away from zero. P-value, the meaning is that if how likely the probability, the likelihood that the actual true coefficient, for example, for temperature is zero. And so if it is truly zero, then means this estimate is not confident, is not reliable. So the lower probability, the better. And such as this is a low probability and this is also fairly low. And so it's considered to be significant. The tag of stars also indicate the levels of significance, such as a single star indicates p-value between 0.01 and 0.05. The highest, which not in this model, are 3 stars between 0 and less than 0.001. And overall, we want the p-value to be less than 0.1 or 0.05, like in this case. So this is now has some significance at the low level, but reasonable. And so those are the elements and metrics that are commonly used to explain, give indication of explanatory power of a model, and also to answer some questions related to how the model explains the variances or how the predictors explain the changes in Y value. And to extend this model to multi-linear regression, one can start adding multiple predictors. The formulations for metrics and for linear least square methods will also need to be extended to account for multiple X, multiple predictors. For example, the alpha Y, which is Y-intercept, is just the expected value of Y, or the when the independent variables are all zero on the line. And to most of the models or most of the data sets will come with multiple predictors. And most importantly, there must be one dependent variable, which is numerical, continuous, or integer. And there can be one independent variable, like in the Challenger model, or multiple ones. Because the predictors can be either numerical or nominal categorical, and packages or function like LM will automatically convert categorical variables to dummy coding, which we will briefly talk about. Other terms that one can engineer, which I will, you will see some examples in the insurance tutorial, and also which is from chapter 6 of machine learning with R. And this is something you should consider to practice and learn to derive and think about including in your assignment 4 as well. So interactions are essentially a term that is coded, that is indicated or expressed as a multiple product of two variables, where V1 and V2 are included as separate individual predictors, or by using star to join these two predictor, both the product term and the individual V1 and individual V2 are considered to be the included in the predictors. Sorry. Okay. There's also nonlinear predictors of variables such as temperature. So if the square term or quadratic term of predictors could predict better, or the other polynomial terms or log transformations of the variables. These are all possible considerations to be included to build multilinear regression models. We talk about categorical predictors, which some statistics literature also call qualitative predictors. And if you have to manually transform categorical predictors to um, numerical variables, which essentially will be 0, 1 variables, this is we call dummy coding categorical variable using dummy variables. If a categorical variable only have 2 categories, then we only need 1 dummy variable to indicate that if it's one case, the value of the dummy variable is 1. If it's the other case, its dummy value is 0. But if a categorical variable such as education and region have multiple categories, such as 3 in case of political parties, party a voter belongs to or a senator belongs to, then we will use 3 minus 1, or we call L minus 1 if there are L factors or L levels in a factor variable. We will only need L minus 1 dummy variable. So 3 minus 1 will be 2. And the first value is always used as reference variable, and like either yes or no. And then, so when dummy is 1, that means Republican is 0. Dummy is dummy is 1. It means that the party is actually Republican. Dummy is 1, 2. Dummy 2 is 1. Then the party is Democrat. When none of this is 1, that's when the third, called the reference category, is the case for the record or for the data point. So in your tutorials or for your assignment, some of the data sets don't have categorical variables, but insurance does. You can actually see the dummy coded, the automatically generated dummy variables for region and for sex categorical variables. Let's use the insurance example from Chapter 6 of Machine Learning with R to continue to look at some concepts and questions and evaluation metrics for regression models. Insurance with patient examples and expenses in another variables. Variable is has several predictors: age, gender, body mass index (BMI), number of children, smoker or not, and the region where a patient resizing, and these are predictors for annual medical expense of a patient. So mainly this then allow us to come back and we look at explanatory questions, and we look at now in this example we will be interested in relationship between insurance expense predictors such as BMI. Is it linear? How strong is the relationship, linear relationship? Since this one now have multiple predictors, so considering synergy potentially that may be from smoker and BMI and could be interesting. And again, whether the performance of the explanations can be general to other data sets will continue to be a question that should be evaluated using holdout data sets. So the model output, model building and testing and improvement will have already been recorded by Yuan Yuan in her video. And this is just an example of the output. And to improve a model like this using nonlinear forms of variables such as quadratic form, log transformation, and interaction terms that we talked about before is something to be considered. And you will see an example of this for age and an example of this in insurance. So something to also further explore when you get to assignment 4. So now it's time to look at, regardless the explanatory power of a model. At the end of the day, our interest is in how accurate our predictions for expenses are. For example, how accurate our predictions for distress count or O-ring values are. So this type of accuracy are not clearly and intuitively indicated using other explanatory metrics that we have seen. So it's time to look at some other metrics. Questions, when we ask questions about predictive power, accuracy comes, and the roles and the importance and the contribution predictors make to improving model accuracy also come in. Comparing methods always important, but more important for predictive power, because some of the models are less have less explanatory power but could be more accurate than linear regression, multilinear regression models. So there is a tendency to, similar to classification, to compare multiple models, multiple methods for generating models. And whether model is overfitted to a data set, that's important. And when you measure errors, and some applications may be more concerned with large prediction errors. It doesn't mean overall the total prediction errors are large or not, but individually the between the actual target variable value and the predicted target variable value, that if the E or the error is large, and whether that, and there are many predictions like that, then if some applications want to recognize that, that's also a consideration for selecting evaluation metrics for prediction accuracy. And so this comes, so that's why that for prediction accuracy, you tend to see more metrics such as mean absolute errors, mean square errors, root mean square errors, and mean absolute percentage error, root mean square percentage error, relative absolute error, and relative root square error, etc. So this, except for MSE, which is now incorporated within here, are the prediction accuracy metrics that we will practice in your tutorials and in your assignment 4. Okay, so since both for explanatory questions and predictive accuracy questions, whether the performance is general across different data set keeps coming in, then if build models and evaluate models to assess the differences in metrics, evaluation metrics, either it is R squared or just the R squared for explanatory power evaluation, or for mean absolute errors, for prediction accuracy. It is always important to consider to use holdout data set first of all, such as when data comes, and don't mix training with holdout data. And and depends on the methods that you use, try to have more testing data sets. So this is a review. Both of these slides were review from classification because this is also supervised learning that use data set that has target variable with given values. The three common methods we introduced, and so far we have practiced two of them, are splitting method that either split, for example, we have seen examples of splitting into two halves, um, or 70%, 30%, or multiple subsets, and random subsampling that generate several pairs of training and testing data set out of the original data set, but randomly change the sampling of training data in each pair. We haven't talked about cross-validation. It's also a similar method for that can increase the number of test sets for evaluation. Okay, we've seen examples already using two partitions, three partitions in assignment 2, assignment 3, in some tutorials. One can think about at what point in time we could consider to generate more than two test sets, and that shouldn't be a consideration until the data set is reasonably large. And random subsampling is something you started to use and start to learn for in the tutorials for assignment 3, and you are practicing in assignment 3. We didn't talk about this too much in class, and I just want to mention that the one consideration of this is that when you compare to splitting method, which always only have one training data set but multiple testing sets, that this random subsampling method will have multiple training sets, one for each of each pair, and using each training set there will be a model trained, and then that model will be tested and evaluated using the corresponding testing set from the same pair. So as a result, that you are actually testing and evaluating whether the method that's being used, for example, C50 or naive Bayesian or regression, linear regression, or other method, the method, when it is used applied to the data set repeatedly, multiple times, whether the performance can be general when it's been tested. And by going for this type of testing approach will allow us to repeat this random sampling and creating multiple pairs as much as we want. But if we create many pairs, then computationally would take a long time. So this, if smaller n is preferred in order to save time and save the demand on our computing capacity. However, if a small n still doesn't give us steady performance, or doesn't allow us to assess the performance at convergence or at steady state, then we should consider to increase it. So when you are practicing, or whenever you have a new application or a new method, or new data set, it's always good to try different n's. So in assignment 4, that's something you should consider and compare. And so if, for example, you compare 10 random sample pairs to 20 to 30 pairs, and the performance is pretty similar, then of course, just choose the smallest n out of the ones that you compare going forward. And you have then some testing result to help support you on that decision on n. So now that we want to evaluate accuracy, um, the recall precision confusion matrix no longer apply when you are measuring the accuracy in predicting numerical target variables. So this 6 are most common choices of uh, metrics for prediction accuracy of regression models, which all, because they are all based on errors between actual target variable numerical value and the predicted numerical target variable values. So every metrics have an E in the abbreviations for that reason. And they, on the left-hand side, all of these errors are measure using absolute terms. So that will convert negative value to also positive value. And everything on this side will convert negative value to positive value using square term. So take a square of the difference of error or residual. So all these are the same, residual error and error or residual, but taking a square term. And this is inside this square root is called MSE, mean square errors. And having a root will bring the value back to a little bit more of the normal scale as opposed to the square scale. So this upper two are frankly most common, include these upper two measures are most commonly used, also because their simplicity. So on the left-hand side, this just only measure the mean, meaning average of average error, absolute errors between predicted value and actual value over n instances or n testing cases or n records. The mean is reflected here, 1 over n for number of testing cases. So here is also mean, where whenever you divide the error measure, total error measures over by n, then that give you mean. And here, taking the mean of square errors inside square root is called root mean square errors. Then out there for a lot of famous context of prediction, for example, Netflix competition for recommender to predict whether someone predict a user's rating of a movie that has not been previously watched, and this was the measure that was used. There is an issue with this measure in that this could vary greatly by the data set, and you don't know how to adjust, compare this MAE for one testing data set, because based on the n there and also based on the actual value of y, this could be affected by the y distribution there. So this other two for mean based on absolute errors, and the other two based on square errors are used to sort of show somewhat of normalized error measures. Here, this is called MAPE, mean absolute percentage error, is to measure the error, which is this term, the error estimated and the actual. In terms of the how the percentage, this error is measured as a percentage of the actual y value. That's what happens when you divide this error by the original actual y or target variable value and multiply by 100 or not, doesn't matter. Just the value will be either between 0 and 100 or 0 and 1, for example, in this case. And it's mean, so it's still average over all n. This percentages will sum up over all cases and take an average. This percentage is squared and summed up and taken a mean divided by n and take a square root. This is the counterpart of this based on square percentage errors called root mean square percentage error. And with the concern of that this could vary by data set, these two start to become more popularly used for comparing and evaluating model generality or generalizability over different data sets, just because different data sets may have different Y distribution. These two errors have one disadvantage, is that because this is expressed as a percentage of actual value and YT sometimes can be 0. For example, in the distress count of the distress count variable of a challenger data set, the distress count could be 0 failures, 1 failure, 2 failures. So when this is divided by 0, then this one wouldn't work. Some sort of smoothing is needed, and smoothing could affect the measure also somehow, and the interpretation. So it's a bit complicated. So these two are actually also quite commonly used to overcome the fact that different data sets may have different Y distribution. And it's called relative here, relative here error. Based on, in this set, this is based on error measure using absolute function. And this one is based on the right-hand side, this one is based on squared errors and inside root. And it's relative, so the numerators are the same as here. But the denominator is no longer just taking an n or taking divided by the actual y value. Rather, it's divided by the variance of the y value. So the y mean and the y value over n testing instances. So this is called relative absolute error. And when this is, so because of these are absolute values, these are square values, so and inside a root. So these are not affected as much. These are not affected by 0, and it's also good to has adjusted the error terms to the variance of target variable. So these are the in Yuan Yuan's tutorials, you will see this code for insurance data set to create, after partitions are created, model is built. These are two simple split models, and testing predictions being generated for the two test sets. Then in M metric, you can generate both accuracy, prediction accuracy metrics, as well as the metrics for explanatory power of a model. And the result of the simplest data, I think the base model of insurance, using insurance data, using linear regression, for test set 1 is here, and for test set 2 is here. The point I want to see is that when you look at them, you look at R, between COR and R square, you can just look at 1 because they are the same. R square is the square of correlation. And they're very close, just difference is 0.01. I don't have any concern the model is general to these two data sets. And if you look at MAE and RMSE, you start to see, oh, there's almost $30 because the unit here is dollars, and $30 difference. And how do I interpret $30 difference? And RMSE, there is almost $80 difference. So the first question is, how do I interpret whether $80 is a lot or not a lot? $30 a lot or not a lot? And likely you can look at it, oh, 30 out of 40. 4,000 is about less than 1%. That's probably not too much. And 80 out of 6,000, it's a little bit over 1%, slightly higher, not terrible either. But it's a lot easier when you just look at this somewhat normalized that have already taken into account variations in the Y values within two data sets, where you see that the difference of point less than 1 here, less than almost 1 here, and less than 1 and 0.5 amongst this, it still shows that this is a good model. Another point I want to make here is when you compare, besides comparing MAE to MAE, RMSE, and RMSE, if you think about why is there the difference here is 30 and the difference here is 80, what does it indicate? That you should think of it from the square terms perspective. When the error, for example, if error is 1 and the error measured using absolute function is same here versus here. But if the error is a larger value, for example, 50, mean absolute here, 50 and then square here, and then depending on the division by different n, whether that will come back down to also 50 or not. That depends on how many, whether there are a lot of large errors. So when this is higher than this, it means that the difference between these two here, between these two is 80, higher than almost 30 here. It means that there are some more large errors between predicted Y value and actual values that are affecting this. So if some models are more concerned with large errors, so and where those may be offset by other small errors in MAE, but not so won't be offset in RMSE, then this root square error type of measures could will be more useful. So to sum up, then that's the end of the concepts related to linear regression, multiple linear regression model building for regression analysis. There are still two other models you can easily, quickly apply. There are hybrid models. There's no need to get into the math, and Yuan have already covered this in the tutorials, and you can take a look, or after this in class, we will go over the use of these two, and then to apply what you have learned in real world, then think about how to use different splitting different model building and model evaluation approaches and different evaluation metrics, and how to evaluate the models using the metrics are something it will be the focus of your practice in assignment 4. Okay, thank you.